Hello, my name is Jan Brugård. I'm the CEO of Wolfram Math Core Developers of SystemModeler. I will be presenting Wolfram SystemModeler 4 and what has been new during the last year.
Okay, thank you very much. So, as Phil said, I hope you enjoyed the dinner and additive public cloud. I will be introducing the new SystemModeler 4, as Phil said. I did a presentation last year on what was coming up with SystemModeler 4. So some of it will be a repetition, but I will take it with new examples. Other things will be new because I didn't present everything. And furthermore, we have released more material during the year. And basically, as some of you will not be that familiar with SystemModeler, I will start with presenting SystemModeler itself with a very basic example. Then I will go into what was new with, let's see, my cursor there. What's new in SystemModeler 4, where we were working on the user interface, documentation. I will just quickly pass that. Then go into new built-in libraries, connectivity and deployment, and show some deeper integration with Mathematica, because that's one of the keys with SystemModeler, the ability to connect it to Mathematica and do some interesting design and analysis using Mathematica. During the year, we also introduced a library store where you can have additional functionality to add it to SystemModeler. So I will present that briefly also. And then in, I think February, might be March, we had SystemModeler 4.1 released, which had a few extra functionality, including combining system reliability with the system simulation functionality that it already had. And at the end, I will show a little bit of how you can learn more. So let's get started by SystemModeler and what it's for. So many of you have seen this slide before. For some, it might be new. It's kind of trying to illustrate which kind of systems do you want to model with something called SystemModeler. Well, it's any system that is dynamic, which is changing over time. It could be an aircraft or an excavator, a robot, the human body, or, well, this thing here. So it can be a variety of things. The important thing is that it can be described in differential algebraic equations. But as a user, you don't tend to work with the differential algebraic equations. You will use with a drag-and-drop environment with icons. Rather than having to focus on the maths, you can focus on the physics, on the concepts, pull that together, and do simulations. If you like, you can go into the equations and study those too. But let's illustrate this with a very basic example. How many here have wondered what a squirrel can do with the machine gun jetpack? Well, so typically I start with a DC motor as the introductory example, but I thought that was not as fun as investigating what will happen if a squirrel would he have a machine gun and try to use that to propel himself up in the air. Some of you might have seen this as a blog already or as XKCD, but still I think it's a very good illustration of how to use SystemModeler. So what I do from Mathematica here, SystemModeler runs standalone from Mathematica, but I can also run it from within Mathematica. So I will need to load SystemModeler into Mathematica, and then I will open this model in SystemModeler. Here we have it. So here you can see we don't see any equations. What do we have? We have a model for a squirrel, for the machine gun, some position sensor, and then a crash detector. And this is done with plug and play of mostly ready-made components from the library. So if I click into the squirrel doesn't exist, of course, in our set of libraries. But the model of a squirrel is really simplistic. Let's open it this way instead. It's just the mass corresponding to the mass of the squirrel and a gravitational force acting on it. So it's a very simple squirrel, can't really do anything. But I guess not having the brain model of the squirrel doesn't make too much difference. It's kind of not that intelligent anyway. So, and in the same way, we have the machine gun and we have the crash detector component base. It's drag and drop, and once every once in a you don't have ready-made components they can drag and drop from, then you make some equations. But let's not go into that. Instead, well, let's do a simulation from in SystemModeler first of this. So I click Simulate. This is converted to a C code, actually, and I can simulate and see the position sensor to see, with one gun shooting, how high will I fly. So we will fly like 9 centimeters, something like that, with one bullet. I can then see, okay, let's say that we have more bullets. What will happen then? So let's go into the gun and say that it has, let's say, 95 bullets. And then it will shoot the bullets in sequence, and we can see here that it will continue to propel. At some point in time, it starts to follow, and then it happens at 70 meters, so I guess it's a pretty decent fall. And the reason why it's falling is, of course, because it runs out of ammunition. So I can actually look at that. I guess, let's go into the gun, and I assume there is something showing, well, let's skip that. Somewhere there is a variable for the number of bullets shot. Anyway, that is how you model and you simulate in SystemModeler, and that could be the squirrel, it could be a DC motor or a vehicle or something like a human body to see the metabolism or something like that. But once you have a model, you can look at what would happen if a human being would try to do this. And then we make a platform of a lot of machine guns and we see how high can we actually propel this. So we use now parameters that correspond to an AK-47, I guess. I'm not that good at machine guns, I must admit. I'm a Swede. We shoot elks, and not with machine guns. So I have all the bullet mass, the muzzle velocity, and so on and so on. And those are just set in as parameters to the very same model, because it's just the very same behavior, just more mass and more guns, more bullets. And then I can simulate this from within Mathematica this time, and I went pretty quickly. It ran a few simulations in parallel. Oh, I already evaluated this. Let's do that again so you can see that. So we can see that depending on the number of bullets I have, the behavior will be quite different. And this is why you have a modeling tool. Because even if this was kind of a toy example, it actually shows something. Who would have imagined this behavior, for instance? That you would be flying up, and then after a while, you will be losing height before you start to fly upwards again and then drop down. We for sure thought it was a bug in our model first before we realized the real physics behind it, which is really simple. And some of you might already have realized what it is. I won't tell it, but you can read it on the blog and download the model and play around yourself to see why is this. But this is why you have models, to see something that is kind of unexpected for you and try to understand why is this going on. How can I use this to improve the performance of my model? How can I propel myself over the Statue of Liberty? How high can I actually fly? Which is the number of guns that is ideal to fly as high as possible? In fact, I can, in theory, fly 155 meters if I have the right number of guns with the right ammunition. I guess there are some limitations to this in balancing and so on. So that is SystemModeler, what it's all about. And now over to SystemModeler 4. One of the things that I won't show that much, but we work a lot on the user interface, especially on the documentation side, to make it as accessible as possible. Adding videos explaining how to use it, having a lot of cross-linking, just as the Mathematica help, where if you're going into one component or one function, there are cross-links to examples where that is used. And there is also inside the tool itself a complete book about the Modelica language, which is used for the models in SystemModeler, that you can read and with examples to understand how to how to do your textual modeling with full advantage, taking full advantage of it. Okay, so it's a lot about having built-in libraries so you can drag and drop as many systems as possible without having to do any coding of yourself. So with SystemModeler 4, we added a digital library. We added functionality to the rotational and translation mechanical library, added some quasi-stationary and fundamental wave, and you kind of see which type of systems you're supposed to model with the different libraries. So the rotational and translational libraries already existed. And the important thing is that you can connect all these together. So when you build the entire system, it's not only the mechanical part or only the electrical part, it's all those together. And that's what's interesting with the new rotational and translation functionality, which I will use and do an example of. So let's import that model to SystemModeler and open it. So this, let's zoom in a little bit like that. This is a mechanical model, so as many of you kind of can see, but it has connections here to heat ports. So we added the ability to model the heat losses in mechanical systems. And this is, of course, very important if you are trying to understand the efficiency of your system. So once you have this model where you have, let's say, a clutch here, and the clutch has some heat loss, where you have modeled, let's say, the surrounding temperature or whatever that you need in order to get that. You can study things like the generated heat. So I'll simulate this from within. I can simulate that in SystemModeler or from within Mathematica. So I do simulation with different, and then plot this drivetrain. Hopefully this works. I changed the entire presentation kind of last night, so I hope everything will work. But here we can see over time, for an experiment here, the heat loss plotted over time. And we can see that there are some points where we're losing a lot of energy, but we're always losing some. And then we can try to understand when are we losing energy, when are we not losing energy. Basically, it's when the clutches are attaching and we have sliding motion in the clutches where we have the most heat loss and so on. But we can use this, of course, to optimize the operation and minimize the heat loss, which is typically something that you would like. But of course, there are other design constraints that might be more important in some cases, and then you have to consider those too. You can also do some things like looking at what we have, how much heat loss do we have for each component in the system. And something going on here. Yeah, hopefully it gives me something soon. And so in this example, we use Mathematica to kind of crunch all variables that has anything to do with heat loss. So we look, or heat flow. We're looking for every variable that has heat flow in it, and then we try to do a pie chart, which for some reason won't come up here. Perhaps I'll skip that. Yeah, let's skip that. I'll go back to that later. Another important addition, and this is really important, is once you have a model, you want to use it in as many ways as possible. Many times that is by connecting it to other softwares or other hardwares. And this is such an important aspect, so I won't show it here. Instead, I will have a presentation later today focused completely on this. But basically, I was planning to open a model where I will show, for instance, how to run this guy and control it from a model. So we will have the control system developed in SystemModeler and run this model where we will be trying to balance this ball here. And this is thanks to a new library called ModelPlug, which is free additional library. And with that, you can create your own experiments like that easily. It could be this one. You will see several other types of experiments that you could be doing for your lab or for home use, as in this case, it was one of our employees that does all kinds of things. We have a lot of kids working at MathCore. They look old, but they're apparently kids. Okay, so system reliability. As you saw, what I was modeling was how something was actually working, when it's working. You can also model things like, which I have presented before, how would something behave if you have some error? For instance, this one that comes from an old blog where we were testing the flap systems of a Cessna Conquest, where we have this model here, where we have a pilot, we have an ECU, flap system, the hydraulic power, the landing gear, and the power plant. So all of those are described in a similar way to the squirrel, just with slightly different components. Actually, in the case of the flaps, it's a lot of the same components as for the squirrel, because it's masses and movements and so on. But anyways, you have this, and then the question was, what happened if we, for instance, had a short circuit in the system? And we could see that there are scenarios where you have that, and I hope that you can see this. If we look at the middle plot here, what that is showing is the red line is showing what the pilot tries to do, how he tries to change the position of the flaps to control the aircraft. The blue is showing what's actually happening. So we can see that in the beginning, he's changing the angle of the flap, and then when he tries to switch it back, basically it's taking off, and once it's taken off, he wants to have the flaps in neutral position, 0 degrees, but that doesn't happen. Doesn't really matter that much because he's just losing flying more inefficiently, but when he wants to land, it's more important to be able to get him in a proper angle to decrease speed. But that isn't happening either, and this is because of an electrical failure. So you can model these types of failures and see what would happen if I have this failure, what kind of scenarios can happen, what kind of sensors would I need to detect this type of error. And this is all fine, things that you have been able to do for a long time in SystemModeler. But what you can do with 4.1 is to use the really nice functionality of reliability that Mathematica has. Oh, that's right. So let's open a model with that. Thought I had a link for that. Cruise control, there. I actually have it here, just, there you go. So here's the system again in SystemModeler, and I will just, so as I said, it looks, if I go into the flaps, it will kind of look similar to what we saw in the squirrel, just more components and some different. We have some hydraulic system, some mechanical system, and so on. But what matters is that we have now a reliability tab here. So the reliability tab, you can set distributions to any component, any system, and describe, for instance, in this case, a reliability distribution. You can pick for any of the distributions available in Mathematica, like sensor distribution, reliability distribution, and so on, and then set some functionality. How does this depend on the different subsystems? In this case, we're saying the hydraulic power, it's hard to read, I guess, from the back, but the hydraulic power and the flaps have to work for this fully to work. Otherwise, the system fails. Then, of course, the question is, how does the flaps, what's required for the flaps to work? So let's open that class, and we can see that in this case, we have a reliability distribution with a long expression of all the pipes and all the different components here. And if we go into a single pipe, that has a failure distribution. So in the class of the pipe, we have this failure distribution, and once we kind of drag and drop it onto our system and connect it, every one of them will have this failure distribution. So we don't have to rewrite this for every single pipe. It's done once, and then of course I can change it if I like to for an individual pipe. It might have a different behavior. Then I can change that description. But this means I have the reliability of the system together with the possibility of actually simulating what would happen if it fails. So let's look at what we would do with this reliability. In the case of the pipe, we would have 3 different fault modes, which is it's leaking, it's restricted flow, or it's completely blocked. That's basically the 3 fault modes that have been modeled in this case. And likewise, the electrical system will have other type of errors modeled. And then we can do things like simulating, I guess something happened, well, simulating the reliability of the different subsystems. So we can see here, get the reliability of the flap system in blue, which is quite reliable. The hydraulic power system is less reliable, and the full system, of course, less reliable than those together because both of them have to work. So in this way, we can realize that the hydraulic power system seems to be in more need of improvements than the flap system. But we can now use other functional Mathematica, for instance, for instance, plotting. There are a bunch of different measures in Mathematica for the importance of different failures or the effects. So, for instance, the structural importance. And then we can see for the individual pipes, which is the most important failure. And we can see here that they have actually these two, the blocked switch and the restricted switch have a very similar behavior in importance, while the leak switch has less importance. So based on this, we can know which of the faults are, from a reliability perspective, most important for us. But then, of course, we want to do the simulation to see which has the worst effect. Because if the effect is not that dangerous, then we might, even if it's very likely, we might not really care. But if it has a great danger to it, then we will care anyways. So the possibility to combine these two worlds together, reliability with functionality, is really important and something that is unique for SystemModeler. So as I mentioned, I can actually show that for those of you that don't know the language behind the scenes. So here we have the diagram. Behind the scenes, there is a Modelica language, which looks like this. It's basically like any programming language, but it's specifically designed for complex systems and engineering systems, biological systems, and so on. So it's not really that hard to learn, but still, you might not want to do that. In many cases, perhaps you are a vivid Mathematica, Wolfram language programmer. Then perhaps you want to do it in the Wolfram language instead and not have to care about Modelica. Then you can do that from version 4. So you can create models from equations. Like, for instance, in this case, I create a model called new model 1, and then a new model 2, and so on. So if I create new model 1 here, we can see it says, okay, we took this state space equation, and it stores in new model 1. So if I go to SystemModeler now, let's do like this. I can see among my use classes, I have this new model 1 here, and I can drag and drop that and connect that into the rest of my system, just as any other component in Modelica. I can then go in, of course, and look at what happened, how is this constructed. And in the Modelica world, this actually is a very simple model where we are inheriting from a state space model and setting the parameters that we gave it from Mathematica. But we don't need to know that. It just happens for us. That could be a transfer model, or it could be equations. So let's take a very simple system of equations, like that one, and then create the model. And we say in this case, let's call it add block, and it will inherit from blocks, interfaces, single input, single output. So in this case, you need to know a little bit about what's available in Modelica, and then you can add functionality that is already available there, inherit that into your model, and say, add these equations to that model, and make it a function of time. So I model that, and yet again, now if I open the add block, I can go into that and see that in this case it inherits something else, and it has the equation to it. And this could be a very complicated expression sometimes, or as in this case, very simplistic. So one of the reasons to use it is that you are already used to Mathematica, Wolfram language, you want to keep there. But there's other reasons too. Sometimes you want to programmatically create a set or like a big set of models, different, for instance, for the fault modes. Rather than having to connect all the different types of combinations of fault modes or whatever how you have modeled it, you can programmatically let Mathematica, by programming that, have it create a set of models. And then you don't have to do all that type. You use like a few lines of code in Mathematica, and it will populate the entire set of models for you. But you can also, from Mathematica, well, this relates more to what I said, you can connect components together. So you can say, I want this type of class using from SystemModeler, set a list of components, call it R, L, A, C, G. Most of you kind of understand which type of system that is. And then we say, connect this using rules. So G.P connect to AC.N and so on. So I can programmatically say how to connect something in using double-gem connect components. So I'll do that, and it works fine, except for one thing, and you will see that soon. The diagram is kind of not that good looking, but it's easy to fix, because you have it in SystemModeler now, and you can try to rearrange, you can try to rearrange stuff, like moving around, and let's do this. Reset connection line. Move around and try to see how should this be arranged to look good. And then you have your system there. Okay, so let's see how I'm on time. Yeah, pretty good. So then during the year, one of the things we launched for SystemModeler 4 was this library store. And the idea with the library store is to add functionality that is quite specific for a domain that not everybody would be kind of interested in always. Sometimes very specialized, but very advanced, like the smart cooling library, which the guys from AIT, which back there have been developing. This is available as a paid library from our library store, yes, as a hydraulic library, where you can add that functionality to your SystemModeler models by buying those. But there are also some free libraries available, like the model plug, which I will be showing later on, where you can do this kind of thing. And the idea is that we will be adding libraries as we go by. So in between releases, you can see added functionality. And that is not only by us. As I said, smart cooling is developed by AIT. And System Dynamics is also a third-party library. Planar Mechanics is a third-party library. Model plug happened to be developed at home by the guy that wanted to play. So in that way, there's an infrastructure now for users to add functionality to SystemModeler by developing their own library, and they can distribute it either for free through our library store or as a paid library. Yep.
Can you use each Modelica library?
Sorry?
Could you use each Modelica library?
Okay, so I guess the question is if you can use all the Modelica. So there's a lot of Modelica libraries out there. In principle, the answer is yes. But the real answer, I have to admit, is no, because there are many Modelica libraries that are not complying completely to Modelica. They have, for instance, Daimola-specific code still, so they have some cleanup of doing. And many are outdated, and those like old versions that we're not supporting. So those won't work either. So there are some restrictions to that, but in principle, yes, you can kind of use others.
At each phase, could you see an overview which libraries are available?
Yeah, well, that's one of the reasons why we're doing this, because that's a very common question. Which can I use? Which can I not use? And it's very hard to say, because those libraries are developed often by a PhD student. And once the PhD student goes somewhere else, the library kind of vanishes, is basically discontinued, but with anyone saying it's discontinued. So there's no future, no development done. So when Modelica upgrades, there's no upgrade to that, and then it doesn't work with it, and so on. So it's kind of complex. So this is one of the main reasons why we created this. In order to piece by piece go curating the libraries and make sure that they're fully tested with SystemModeler, that we can guarantee not only that they're working, but also that the documentation is actually good, the examples available are good, so we have quality measures on what you have to provide in the library in order to be able to submit it to our library store. And then also it has some other functionality where it actually comes packed, where you get it, you double click it, it installs, and everything is automatically, and you can add like descripting videos, documentation, and so on in a very nice format. So there are several reasons for this store.
Could you combine binary models with this?
Yeah, as long as it's Modelica, true Modelica. But Daimola used to have, because Daimola came from a language called Daimola, and they have some Daimola artifacts in many of the, let's say, Daimola models. So depending on that. Okay. I won't really talk too much about the different libraries, but let me just show the hydraulic library quickly from the library store. So in the library store, you will see the libraries describe the price or whether they are free. You can request a trial, and in this case, you can see it's 645 pounds if you're based in Sweden. You can change to whichever country you want to see the price for. And then you will see the key features, but you will also have examples for how to use it. Where is it applicable? So for instance, I could go into motors and valves and see that example. And then I can see a description of motors and valves, how can you use that, what kind of analysis can you do on that, and so on. So here you can learn about the different libraries and get an idea if this is something for you. And if it is, you can request a trial or buy it directly. So that is a very quick summary of what's new in 4.1 or in 4 and 4.1. As I said, I will show more on connectivity part later today at this very same room, I think, at 14:45. But I will also like to show some other resources. I just showed one example, but actually there are a bunch of different examples. Not all of you are from the field of modeling squirrels or aircrafts. Perhaps you are more interested in other applications. Then you might want to see examples from your specific field. Then you can go to the industry examples, and you will see kind of the different fields, whether it's, let's say, meal simulation, which is quite different from what we have done now. You can go in and see several different examples from life science. You will see the example, and in some cases, I think this one, for instance, insulin signaling, the model is downloadable. So you get a description of the model, but you can also download it to run it with a trial. I had already opened it before, I see. And when I open it, I can see here is, for instance, a notebook with a description of how to run this and some experiments and so on. that you can do whatever you like with, so you can use that. If you want to have it to deploy it on a class to do some kind of example, you can do that. If it's just for learning yourself, you can do that, and you can modify it in whichever way you like. So this is a great resource in order to understand how it applies to your domain. Okay. We were pretty bad at producing blogs before. This year we have added quite a lot. So these are the blogs that have come up for SystemModeler during the last year, since the last conference. And in general, I would say these are we have the squirrel there, as I said. But in general, they are of a more serious kind, where it's a real life topic that matters for some domain. Like, let's say, this one here. Can AstraZeneca count on your liver? That one is showing how AstraZeneca is using SystemModeler in order to, together with an MRI scan, analyze your liver. So rather than, nowadays, to analyze the liver, you have to take a biopsy. And that is a pretty intrusive, and it has a lot of its costs and complications, and it takes several weeks before you're up and running in full shape again. But here instead, they put you into an MRI scan, do image processing in Mathematica, use that images to correlate to models, simulate, and understand the health condition of your liver. So in that way, you can diagnose the liver without having an intrusive biopsy, which is pretty cool, I would say. For more technical questions, I think this is general for the entire Wolfram community. So Wolfram community was launched, I don't know exactly. Anyone knows, when was Wolfram community? It's like 2 years ago? Something like that? Yeah, we take that afterwards, yeah, soon, yeah. So I just wrap up with the Wolfram community and then now. So the Wolfram community has a lot of different forums, for instance, for SystemModeler. So I recommend this for anyone that is trying out and have questions for a specific area. And we are, both the community themselves and we at the team, are pretty eager to answer the things that comes into the community. So that's a very, very good way to get your questions answered when it comes to technical questions while trying out the software. It might be, how do I model this? How do I model that? Do I have an idea for that? I tried this model. I don't get it to work. You publish that model, and then somebody will come out there and help you. And that goes for entire Mathematica. I think it's a very good resource that more people should use in general for the Wolfram products. And then, as I said, later today, I will have another presentation. And with that, I wrap up and thank you and take some questions. Thank you.